Hello, and in today's ATmega328P Programming, we're going to be doing the TWI interface. This is also known as the I2C interface with a real-time clock, specifically the DS1307 real-time clock. Let's have a look at the schematic. The rest of the schematic is basically the same one as usual. For the RTC, we have our SDA line connected to the SDA of the ATmega328P, and then our SCL line connected to the SCL line of the ATmega328P, and then we have two 4K7 pull-ups for the two data lines. And we are going to be displaying the date and time via the UART on PuTTY. Okay, now let's have a look at the data sheets. The DS1307 real-time clock. It's an I2C clock. TWI interfaces are compatible with I2C. Okay, then we are going to skip to its registers. Now it has 7 registers associated with the date and time. We are only going to be using the first 7 registers. So from register 0 to register 6 we are going to be using. Now some notes are bit 7 of register 0 and then bit 6 of register 2. Okay, now the CH bit in register 0, when this bit is set to 1, it is disabled, so we are always going to be writing 0 since we want our clock to be running. And then in register 2, when it is high, it is 12-hour mode selected. We are going to be running in 24-hour mode, so this bit will also always be 0. And then we have the address for the device that we are going to be using. This is the right shifted by 1 address. We are going to be using the base address and then later shifting the address, so we are going to use the first 7 bits and then going to be shifting them by 1 to the left and then adding our R or W bit at the end. Okay, then we have how we write data to the DS1307. So we do an I2C start condition, we write the slave address to it, and we write a 0, receive and acknowledge. Then we write which address we want to write to. We wait for an acknowledge, and then we can send data and get an acknowledge on each individual data step. And then we send a stop to stop the transaction. Now, how we read data, we send the start condition, and then we send our address, and then we send a 1 through to indicate that we want to read data, and then we just read the data through from whichever address we were reading from last. And on the last one we set a not acknowledge and we send then a stop bit. Now the more standard method is for reading data is first we're going to send a start condition through, and then the address with a write bit, we write to which register we want to start reading at, and then after we have received both our acknowledges, then we send a repeated start. So we send the normal start condition again, we write that address and we say we want to read the address, we get our acknowledge, and then we write data into whichever address we want to, because usually if you set it to address 0, then the next read will be address 1, 2, 3, 4, 5, 6, 7, 8, and so on and so forth. And until you get to your end of your data, your last data you want to receive, you will send a not acknowledge and you will send a stop bit. Okay, now we have the ATmega328P datasheet for their 2-wire interface or TWI interface. It can do up to 400 kilohertz data transfer speed, so your usual maximum of I2C, and then they have compatible with Philips I2C protocol. Okay, now we are going to skip ahead to the registers. Okay, so our first register is the TWI bit generator register. This is your divider register for the clock frequency. So depending on what you set this whole register as, it will determine what the speed is you are going to clock the clock line at. Then we have the control register. So in bit 7, this is the TWI interrupt flag. You have to manually clear this flag by writing a 1 to it before each transaction. Then we have our TWI enable acknowledge bit. This enables you to transmit and acknowledge when you receive data from the I2C device. Bit 5, which is the TWI start condition bit. When you write a 1 to this bit, it transmits a start condition condition on the TWI bus. And then we have TWI stop, which again write a 1 to it and you transmit a stop condition on the bus. We have the TWI write collision flag. We are not going to be using this one. This is used in multi-master mode. Then we have the TWI enable bit. This turns on the I2C driver on the ATmega328P. And then we have bit 0 for the TWI interrupt enable. This one will enable the interrupt when you write a 1 to it. And you have global interrupts enabled. Then we have the TWI status register. Bit 7 to 3 is read-only bits. These are status codes that come from the internal state machine of the ATmega328P. We are going to be talking about this a bit later. Then we have the bit 1 and bit 0, which is our prescaler bits, which is used also in selecting the clock speed of the TWI interface. We are going to be using a prescaler of 1 with our 16 megahertz clock. Then we have our TWI data register, which is used to transmit or receive data. So if you write data to it, it's going to send this data over the I2C bus. If you read from it, you're expecting data from the I2C bus after an acknowledge. Then we have the slave address and the slave address mask registers. These are relevant to I2C slave operation, which we are not going to be handling here. Using the TWI, here they basically give you a basic setup of how you send data on the I2C bus. SLA plus write means slave address plus the write or the read bit. In this case, W will always mean write, and then you get your acknowledge, data, and stop. And then they give you some sample code over here. And then we get to the master transmit mode, which they show a basic circuit diagram over here of how the devices can be used. But what we're interested in is how the registers are set up. Now an X indicates do not care state on this bus. So whatever those bit values are, they do not matter. So this first one will be your TWI control register needs to be this value to transmit a start condition. And then they give us a status code that comes back for it. We will be getting to the state machine eventually. Then we need to transfer our address bit to the TWDR register, which is the transmit register, and then we just need to clear the SDA bit, which is automatically cleared for us after we have received our status code of 08. And then after we have transmitted, we get one of the following 3 status codes. Data packet should be transmitted, and this is done by writing to the TWR. And then they also say TWR must only be written when TW interrupt is high. So always write a 1 to TWINT before you do anything. So this is your data transmit, and then we're just going to sit and acknowledge every time we transmit data. And yeah, they also say it is repeated, and then we can either send a stop condition, which is this one, or a repeated start condition, which is this one. And then they give us all the status codes. So if we have a successful start, we get 0x08 as our start condition. We get 10 for a repeated start condition. We get 18 for a slave and a write bit has been transmitted, and an acknowledge has been received. Then we get status code 20, which is a slave and a write has been transmitted, but we have not received a acknowledge bit, which is an indication of an error on the bus. Then we have 28, which is data byte has been transmitted and an acknowledge has been received. This is your normal condition. Then we have 30 on the bus, which is a data byte has been transmitted and a not acknowledge has been received. If not acknowledge has been received, this is an indication of an error on the bus. And then we have 38, which is arbitration loss in the slave write or a data byte. This is only relevant in multi-master mode, where you have maybe 2 or more masters that are trying to communicate at the same time. Now, the TWI state machine is smart enough to sit and wait until it gets a stop condition from another master before it initiates its start condition. And then I have a diagram of what your typical state codes will be. Like, you send a start, you get 08 back. You transmit your slave address plus a write, and you get an acknowledge, you get 18 back. And then data, and then acknowledge, you get 28 back. And then a stop condition, which has no state code. code. And then we have all the derivatives of what happens when there is a fault. And now something of note is, you'll see on any of these error codes that they will indicate that you need to send a stop on the bus. Now, when you send a stop condition on any state, it resets the state machine in the ATmega328P. So then you can start again from the top with your start condition. So if you detect any error, just immediately send a stop condition over the bus. And then we have master receive mode. Then we have our standard start condition here. And so basically you send a slave plus a read via the TWIR, and then you get your acknowledge and your transmits back. And then here where they say the acknowledge, you need to write the EA bit to 1 when you want to receive an acknowledge, and you need to unset it when you do not want to receive a acknowledge. And then I have the status codes for receiving on the TWI bus, which is 08 for your start condition, which is the same as the previous state machine, 10 for a repeated start, again the same as the previous one, and then I have 38 for an arbitration loss, so the master device lost control over the I2C bus during a transmit or anything like that. Again, not applicable because we're using only single master mode. Then we have our slave address plus read, and we have received an acknowledge, which will give us 40. Then we have 48, which is not acknowledged, plus slave plus read, which is indicative of a error code. And then we have 50, which is data has been received and acknowledged, and an acknowledge has been returned. This is used while you're sending multiple data down the line. Then we have status code 58, which is data byte has been received, not acknowledged has been returned. This is when you end your transmission on the bus. When you stop receiving data, you send over a not acknowledged to the slave device, and then you send a stop afterwards. And then I have a diagram of the various state codes, which you go through. You write your read bit, you write your data, you get your data back, you get an acknowledge, you send a not acknowledge at the end, and then you send a stop. And then again, all the derivatives of the error codes. And again, if you get any error codes, you send a stop bit over the bus, which resets the state machine. And then they have the slave modes, which we are going to give a skip over. They have their separate error and status codes. And then we have two values, which are miscellaneous data values. F8 indicates an empty status register. There is no available data on the status bus. And then 00, which indicates an error in either the start or the stop transmission. Okay, now let's get to the coding. Okay, now so the base program setup, I already set up the .h files for this and the C file, that's separately. I have the standard LEDs just for indication that we are actually running. I have an ADC for blinking LEDs, holders. This is the basic stuff that we had for the timer. Then we have an RTC interval value. This is what we're going to use to indicate we want to read from the I2C bus. We're going to make it reads every half a second. I have enabled the trim pot just for indication's sake. Timer 0 is in it for our millis functions. We send over a UART string. We do an ADC conversion for our initial delay. We have our holder millis, and then we timestamp for our RTC read interval. So now we go to the .h file, and the first thing we want to do is we want to define our status codes, and I have pre-written them out here. So we can just paste them in. So we have our state for TWI start. We have our TWI restart status code, TWI transmit address acknowledge, TWI transmit address not acknowledge, TWI transmit data acknowledge and data not acknowledge. And then we have again our receive address acknowledged. We have our received address not acknowledged, data not acknowledged for receive. We have our general error code, and then we have there is no status code. And then next I have a few custom error codes I want to add in a numerator. So we have TWI OK, which returns an OK value for us. We have TWI error start. We have TWI error in a restart. And then we have a TWI error not acknowledge. And then I'm going to add another variable for a timeout. Now this timeout is a 1 millisecond timeout, which is a hard timeout based on the cycles of the clock. So if I have a counter that counts up to 16,000, it's an error code. The first function we want to create is the TWI init function, which starts our init. I forgot something. Okay, then our final bit on the datasheet is going to be the bitrate generator. Now this bitrate generator, we have our prescaler value, which we already set as 1. Then we have the value we want and then the rest we have standard. Now we will work this back. We want the TWBR register. This will be our FCPU divided by FSCL minus 16, and then we take this entire thing and divide it by 2 to get our TWBR value. Okay, now let's get to the code. Okay, so the first function we are going to be writing is the TWI initialize. So we say void TWI init, and it is a void function, and then we declare a variable of uint32 underscore t. We just call it gen underscore t. For temporary we set it equals to 0. Then we say gen t is equals to f course CPU divided by, I forgot the variable in here, that's going to be a uint32 as well, and we are going to say speed, and this is going to be our clock speed of the TWI bus. And then we take if CPU divided by the speed, we minus it by 16, we encase it in a bracket, and we divide it by 2, and then we encase that also in a bracket, and we say and 0xff to turn it into a uint8, and we say our TWBR register, so our baud rate generator register for the TWI is equals to gen t and 0xff, just to make sure that we are inserting a uint8 value. Then we have our TWCR register that is going to be equals to 1 shifted by the TWEN bit to enable the TWI bus, and then we have our TWIE bit set to 1 so that we enable the interrupts, and then we're going to have our ISR function for our interrupt, and that is going to be pointing to the TWI vector, and then we declare a global volatile uint8 underscore t, and we call that status equals 0. Correct my spelling, status, and that is by default going to be equals 0xf8, so a no state, and then status is going to be equals to the TW status register and 0xf8. All our status codes are going to come from the TWRS, and all the status code are already shifted for us. So now we have an interrupt that will give us the current status code for us. And then something we can add to the TWI bus, which I am not going to be using, but if you do not have external pull-ups, then you can do the following piece of code to enable the pull-up on the TWI pins, so your SDA and your SCL pins. Okay, our first function is going to be the TWI start, and that's going to be a static function, so only the C file can use it, and it's going to return a uint8, and that's going to be TWI underscore start. And it is going to take in void parameters, and that is going to be the TW control register, and that is going to be equals to 1 shifted by the TWINT, so we set the interrupt flag high, then we enable the TWI start, so STA, and along with that we have our TWI enable, and also we just copy our interrupt enable from here, and this will now generate a start condition for us. And then if we have our start condition, we say while status not equals the TWI start macro, we wait for the status bit, and finally we will return TWI underscore OK. Now in the while loop we are going to set a timeout, so we are going to have a uint16 I equals to 0, and I will increment by 1, and then if I is greater or equals to TWI timeout, then we return TWI error in the start. We are going to generate a start condition, then we wait for the interrupt to get the status, and then if the status is TWI start, we return TWI OK. If we have waited too long, then we return TWI error start. Then we have our next function, which is going to be the stop, so that's going to be static and it's going to return nothing. Then we call it TWI stop, and it takes in no parameters, and that is going to be our entire control register, and it's going to be TWI STO for the stop condition. And then we duplicate our start function over. This is basically identical to the start function, except it will wait for the status code of rstart. Next function is going to be static. It's also going to be a uint8, and that is going to be TWI ADDR ACK. So our address acknowledge, it's going to take in void parameters. It's also going to take in a uint16 for our timeout. We basically duplicate this piece of the function over, and the only thing that changes is what we write to the control register. And that is going to be everything except our start and stop. So that is going to be set the interrupt flag, enable the TWI driver, and enable the interrupt. And then we wait for TWI transmit adder acknowledge. Then we duplicate this function again. We call this the data acknowledge, and that is going to be the data ack state for a transmit. Should be changing the functions to TWI adder write, and then the next one will be data write acknowledge, and then we duplicate this function over. And this is going to be the ADDR read acknowledge. So this is our TWI receive, and that is going to be ADDR acknowledge that we are waiting for our read acknowledge. So we have TWI interrupt flag enabled, we have our TWI driver enabled, and we have the interrupt enabled. And we get to a bit of a different function, which is our receive data, which is TWI data read ack, and this is going to take in a uint8_t and a ck for acknowledge. Okay, now this is fairly similar. We are just going to say if ACK not equals 0, then we want to transmit a acknowledge from the master device. So we add in one shifted by TWEA, so acknowledge, and then we say else. The standard one without our acknowledge receive. So this one we TWI receive data acknowledge, and then our status will be again here, but the difference is when we don't want an acknowledge, we wait for the next signal. So now we have all our base stuff, and we can add a uint8 function, and that is going to be TWI read, and that is going to take in uint8_ADDR. That is going to be our device address. Our next parameter is going to be uint8reg for the starting register where we want to read, and it's going to take another uint8, which is going to be a pointer to our array of data that we want to receive, and then lastly a uint6, and that's going to be our length of data that we want to receive. So we add in also a uint16_ti equals 0. So this is going to be an counter variable. We add a uint8_t and we call it ERR, and that is going to be equals to TWI_OK as the initialization. So for a receive, we start with error is equals to TWI start function. Then we say if ERR is not equals TWI OK, then we return TWI OK, and we send through a TWI stop to reset the bus and so forth. Okay, so now that we have the start condition, we need to send the address of the device over the I2C bus. So we see TWDR is equals to the address, so ADDR that we pass in, shifted over to the left by 1 bit, and then we OR it with 0. The 0 is not necessary here, it is just there for readability in code. Then we duplicate over our error code. Then we change the function to TWI ADDR write acknowledge. So this tests for a write acknowledge. If it doesn't get its write acknowledge within the timeout period, stop the bus and return the error code, which I see now I have not correctly done. Then we want the TWDR register equals to the register we want to start reading at. Then we duplicate this over again. We say the data write acknowledge. Then after we have written where our starting register is, then we want to do a TWI restart. Then we copy the error code as well. And we set it equals to error. So it will restart the TWI bus. Then we copy our block for the address. And our address is going to be ORed with ones because we are going to want to read from the TWI device. And this is going to be our read acknowledge test. Again, if error code return. And then we start a for loop, and it's going to be I equals 0, I less than len, I incremented by 1, and we say error is equals to TWI data read ack, and that is going to be 1 because we want to receive and acknowledge. And then we also add our error code test. And we say data brace I is equals to the TWDR register once we have received and acknowledged. And this is actually going to be len minus 1. We want an acknowledge every time we read except on the last transmission byte. Then we can duplicate this code over. And then we send a not acknowledge, and I is going to be 1 greater than len minus 1 when it exits the for loop, so we can just say data is equals to I. And then we can send at the end TWI stop. So now we copy the function prototype over here, and this is going to be our TWI write function. And something I forgot, we need to return TWI underscore OK at the end of the function, or we can just return error, which is actually a simpler one. Then we create basically the same initial variables up top for our write function. Then we go and we duplicate our TWI start, our address, up to where we set the register that we want to start reading from. We paste that in, and then we create another for loop, effectively the same for loop as previously, except now we are writing data. So we invert that our data I is equals to the TWDR register, and len is not going to be minus 1 in here because we are just writing the data. And we take our data write acknowledge and we throw that in there. And simply at the end we call TWI stop. So now we need to add these functions to the .h file. So we first add TWI init, and then we add TWI write, and we add TWI read. Okay, so now we go to our main file, go to the top, hash define, and we say RTC underscore ADDR, and that is going to be 0x68 as the address for the DS1307 RTC. Before we enable interrupts, we are going to initialize the TWI, so TWI init, and we initialize it with 100,000, so it's going to be 100 kilohertz interface. It can also be 400 kilohertz, whatever floats your boat. We are going to declare a uint8, and we are going to call it RTC underscore data, and that is going to be a total of 7 bytes. So we are going to have 7 registers. The RTC is encoded in BCD, so hex values are going to be the numbers. So if I write 0x50, it's going to be the 50th second, and then 0x59, that is going to be 59 minutes, 0x23, that is going to be the 23rd hour, 0x07 as the 7th day of the week, and this is going to be the 31st day of the month. And then it's going to be 0x10 as the calendar month, and then the last one we only use 2 digits, and that is going to be 0x20 for the 2020th year. Okay, so before we do our RTC interval, just correct that spelling quickly. Then we are going to write our RTC, so that's going to be EER TWI write, and this is going to be our configuration. So we get the RTC address as our first input. We are going to start at the 0th address, and we are going to give it RTC data, and that's going to be size of RTC data as the length. And then we test if the error is not equals TWI okay, then we do a printout, which I have pre-prepped here. So this printout just basically just tells me, hey, this is the line number and this is the error code that it spits out, and it prints and it enters a blocking while loop infinitely. So it will tell you what the error is when you print it out. And then in our main loop we create a if, and we take our millis end, we say our current RTC interval has run for 500 milliseconds. Then read the RTC again, because the RTC only takes once a second, so you can read it 2 times a second to ensure the value is good. Since we've expired, we just reset our millis. Then we take basically our RTC write function, paste that in, we change it to the read function. This will now read 2 times a second our RTC data. And then I have pre-prepped a printout over here, which is going to print out the year for us, the month for us, the date, the hour, the minutes, and the seconds. The only one I left out is the week, and you can see that by RTC data 3 being missing. Now let's program the ATmega328P. Okay, now you can see I have the RTC module here. If I press reset on the ATmega328P, you can see the LEDs are starting to run independently. In the top left here, you'll be able to see the current date and time counting up once a second. If I reset it again and we wait 10 seconds, you can see it rolls over the date and time and the month for us. The only one I didn't include is the year, but that is not, if one works, the rest will work as well. And that's an introduction to using the TWI bus, also known as the I2C bus on an ATmega328P. A like, share, comment and subscribe is always appreciated. The code will be on Git. Thank you. Have a nice day. Okay, now you can see I have the RTC module over here. Oh, no.